you so much. So let me just share my screen. And thank the organizers for giving me the opportunity to speak about our work. And I've been introduced, I didn't hear it, but my name is Danica Kragic and I come from KTH in Stockholm. And today I'm going to talk about robots learning to perceive, interact, and collaborate, and give you a little bit of both the overview of the work that we are doing, but also I'm gonna go in depth with a couple of works that we have done recently on this particular topic. Now, to just start with a little bit of an idea and perspective on the research that we are doing, I'm going to show you a couple of videos that show the technical systems or the hardware that we also work with. So most of the work is demonstrated and assessed on physical systems, robots that move around in the environment and are equipped with various types of sensing. Most of our robots have dual arm settings, so that to some extent we can study also transfer between dual arm activities in humans to robots. And the tasks that we are considering might be tasks that are more of industrial nature regarding, for example, tasks that we would need to automate in a warehouse setting, but we study it from the perspective of multimodal perception, learning, planning, and so on. Another example, and the work that we have started to do a couple of years back, is also deployment of various types of machine learning and perception techniques that allow us to work in high dimensional spaces and interact with rather complex objects, such as clothing items that are deformable in nature and that in general have an infinite state. Where the planning then we need to generate on robots that has to do, for example, with learning how to fold clothing items, needs to be addressed from the perspective of lower dimensional representations, latent space learning, encoding of motion strategies in some latent space representation, where we use variational autoencoders as one of the representation techniques, and so on. So I'm going to talk a little bit more about that. So the red line or the red thread in our research is that we try to, as I said, do and demonstrate everything on real physical systems, and also address problems such as robots performing in natural environments, so no special lighting or anything like that. Base the control on multisensory feedback, and in order to be able to do that, we borrow and develop methods that are more than contributing to the machine learning community in order to be able to do this also in real time. Another part that is for us very important is physical interaction between a human and a robot. And in this particular setup, we look into, for example, how the robot and the human can jointly coordinate various types of tasks, such as carry something jointly, where we address the problem partially from the control perspective. So how to signal in a way through small motion and dragging from the robot side to show the human or inform the human that robot is maybe close to coming to a joint limit, but also from the HRI perspective. So what would be needed in terms of dialogue-based interaction between a human and a robot, so the robot can signal certain things, and also how can the human understand what are the actions that the robot should be avoiding, again, for the joint limit, from the joint limit perspective or anything in that direction. What I think an interesting scientific question, of course, here is how do we ground perception from the human and the robot side in some common representation? And this is something that we are currently addressing in our research. And then the final video before I go into some of the details relates to tutor student scenarios of various types. Here we are thinking about the robot being, for example, a third hand, trying to understand what the human needs help with, or a human using natural language processing and dialogue-based interaction to instruct the robot what it needs help with. But long term, we would also like to develop systems where the robot can potentially also act as a teacher. And by looking and understanding the viscosity of the dove that the human is building or interacting with, it can provide information to the human. Well, I think that you need more flour in your dove, for example, because the viscosity is too low and so on. So I think that there are many interesting problems here from both, as I said, HRI perspective, but of course, in order to be able to address those more kind of like high level interaction and dialogue based interactions, the robot needs to have an excellent perception of the current state of the environment, partially from what the human is doing and how the human is using his or her body to interact with the environment, but also how the actions that the human is performing result in a potential change state of the object. And I think perceptually it's extremely difficult here to assess what types of forces human is using and whether the robot should instruct the human to press harder or press less, or what does that mean for the human, or to what extent we can understand that maybe dove is too hard and needs more fluid and so on. So, and perceptually just through computer vision or through visual sensing, this is not always possible to do. And this motivates a lot of work that we are doing on multimodal sensing so that we can also, or the robot can through touch, through force torque feedback also understand something about properties that are not extractable directly through vision or visual sensing. We also work very much on trying to understand human perception of robots in collaborative tasks. So this is one of the experiments we did together with neuroscientists, where we looked into what happens in the human brain when a human and a robot perform a task that has a joint goal. It's a simple maze game here. So the robot and the human are controlling the position of a ball that needs to be brought to an opening. So they have a joint goal here. And then we want to understand to what extent, how much time the human, for example, needs to be trained in order to achieve the goal with a robot in comparison to a human or another human. And to what extent various types of actions, like if you have a little bit a nervous robot that moves faster or a rather slow robot that doesn't follow up, how does the human compensates for this unexpected, in a way, behavior that comes from a robot? So there are many interesting problems here that one could study, but also just try to understand where and what to measure when it comes to the then EEG measurements and so on. Now, I'm not going to go through all the details, but these are just some examples of the works that we have looked into and published regarding the previous videos. And what I wanted to say is that apart from, again, looking very much into HRI aspect of the work, we also work with low-level representational learning in terms of how to address problems of dexterous manipulation, using latest deep reinforcement learning techniques where the more classical control methods cannot provide us, or we don't have the analytic model because the tasks are maybe too complicated and so on, but also work very much with various types of geometric methods that have to do with trying to understand the physical aspect of, for example, contact level grasping, and to what extent we can defined representations that can result then in real-time planning of various types of motion tasks. And some of these I'm going to go into in a little bit more detail. Now, what motivates most of our research? I, as you, very much like to reason how I think when I perform some of these tasks. And whichever of these you choose, it's extremely difficult to find an example of a robot today, almost impossible, that can execute any of these tasks in natural environments. And apart from, even if we would be able to build a robot that can comb somebody's hair, do sewing, do cutting and so on, it is extremely difficult to then transfer the knowledge of the representation needed for this task to, for example, washing the dishes. What motivates then our research are these contact-rich tasks and especially the need for interaction with objects that are deformable and also that need to be interacted with in various types of media. So why is this important? Well, it's important because the friction coefficients usually change. The friction coefficients will affect the stability condition of a grasp, the way the robot needs to adapt to these changed conditions. And most of those attributes, such as, for example, friction, will not be directly measurable by any of the sensing that we have available in robots today. We can say, well, humans don't have that understanding of friction coefficients, and we can't either communicate the right level or what the friction coefficient is, and we can still execute all of these tasks. And that motivates also then the use of machine learning methods and data-driven methodologies, where not necessarily we need to have the exact analytical model of the physical properties of various types of tasks, but more data-driven methodologies that are solving various types of regression tasks can be applicable in settings like this. To give you an example, what tasks or problems one might then need to address when it comes to contact-rich tasks, it might be adaptation or gating of the fingers of the robot, such as in this example here. If the weight of a deformable object changes, so this is a plastic cup, and well, one way of addressing when the weight changes, the object starts to slip from the hand because it's the weight increased. And the natural way of compensating for that might be to just apply higher force, so hold the object firmer. The problem is that the object is deformable, and also it's very easy to destroy these rather expensive sensors. So there is an upper bound on the force that we can apply. So what we look into is how we can apply finger gating, so change the way the object is held in order to compensate for these external disturbances, change attributes of the object such as weight and so on. So this is an interesting problem. To what extent we can then develop this real-time strategies, as you see here, where one of the fingers changes while keeping the stable grasp of the third, or with only two fingers and so on. So this is one set of problems that we are looking into, and to what extent, again, the feedback from the sensors that can here measure the forces, the vibrations, and many other parameters can be integrated also with external sensors, such as, for example, images. Another problem, such as this one, a highly dynamic problem from the perspective of teaching the robot of how to throw a ball. And I think that we can draw a parallel here to humans playing sports. You know that it takes some time to train how to swing a golf. How to basically learn how to play golf or tennis. So we also need to train a lot in order to build this kind of like a model of our proprioception. or in muscles. So here we are looking into problems of how to build then systems where a robot can directly from then testing and getting a terminal reward of just it was a good throw or a bad throw, with minimum number of examples, learn what a good throw would be. And I'm going to concentrate a little bit more on the details of how we can then think about effective representations in order to be able to do this on robot with rather few training examples. So we talked a little bit about, or I talked a little bit about the hands and the interactions with the world. And I started to think a little bit more about this problem almost 10 years ago when I was thinking like, well, if we can't build hands that have the same dexterity or the same capabilities as humans, can we at least study or understand what we can do with available robot hands? And most of the off-the-shelf robust robot hands only have 2 fingers, basically look like very simple pickers and so on. But we want to understand from the perspective not only what the hand can do, but also what we can do with the motion of the arm and how we can compensate for some this low dexterity in the hand and still compensate or demonstrate some of the capabilities humans do by using just in-hand manipulation. So we started with some scientific questions that we wanted to understand from the perspective of representation learning. How can a robot or a human interact with the world if the hands have less, more, longer, shorter, no fingers? And so we just wanted to understand, so if we don't have the same dexterity or the capability, can we understand or represent what is still doable with this type of hand? And then it showed that this was very interesting, not only for the, of course, robotics community, but it was also interesting from the prosthetics design. So, for example, how to build prosthetic hands, where to put the actuation, looking into the length of the fingers and so on in order to be able to keep as much of the functionality, but with lower degrees of freedom in comparison to a human hand. And then it also got interesting for the teleoperation and gaming community and so on. So this is why we also stayed and are still addressing some of these very interesting problems. But to show you, let me see if I can go back. Already almost 10 years ago, we could demonstrate that we can put this into the context of understanding interactions that humans usually have with objects in natural environments. So this was not a sped up video, but already 10 years ago, we could demonstrate that with very detailed hand tracking, we could also predict what types of tasks human is intending to do, because we want to understand the intention and how the preparation and the movement of the fingers also gives us a lot of information about what type of object the human is to pick up or what type of grasp the human is preparing to use and so on. And this is interesting. Now, if we go back to those collaborative tasks between human and a robot, prediction is very important, because if the robot is to effectively collaborate with a human or comply to something that the human is about to do, we want to have some form of a prediction model that tells us what the human is going to do next, so that this interaction can happen in a natural way. And I say natural because this is what we exactly observe in humans. When we collaborate with another human, we have a possibility of predicting what the human is going to do next, and use that in then achieving an efficient collaboration with another human. Now, going back to this type of interaction tasks, grasping in particular. We find it interesting from several different perspectives: control, machine learning, perception, HRI, as I said, but also because the majority of human manipulation tasks are contact-rich tasks. In most cases, we will be interacting with something that is either rigidly placed in the environment, use it as a support, or we will manipulate it with either hands and arms or other parts of our body. When we compare contact-free and contact-rich tasks, of course, contact-rich are more difficult to model because we do have exchange of forces and energy. There is high dynamics or complex dynamics usually attached to them. And it's extremely difficult to demonstrate any of these tasks without taking into account both the task and motion planning, real-time feedback control, and then also taking into account that some of these need to be data-driven from the representation, again, point of view, because the state space of most of these tasks will be rather complicated. And for that reason, again, we need real-time and multimodal perception that is then allowing us to do relevant control. And we need to address the way how we model complex physical properties that are not directly measurable, as I already mentioned, for example, friction. Now, some of the then application area, apart from interaction, we are thinking very much about assistive dressing and thinking about tasks. How would it be for a robot, again, with two arms, to pick up a clothing item, bring it to a position or a pose from which it can be safely put over somebody's head. And I think that most of you have, of course, dressed yourself, but also helped other dressing kids and so on. And this green round thing here is representing a head, but as you can see, it's not moving. Now, from the control perspective, this is a very interesting problem. Even if we have found a way of solving the perception problem and finding the hole and so on, how to wiggle the object that is elastic in a good way over somebody's head while potentially that head is also moving, I find it a very interesting and a rather challenging problem. So I think that these are some of the things that motivate a lot of things that we are right now doing with clothing items, because we need to understand also the properties of those clothing items that go, again, beyond just the material, but that we need to look into the material properties. Apart from, of course, assistive dressing, this will be very important also for how do we recycle items, how do we potentially reuse them, and so on. So to give you a little bit of an idea then, how do we address or approach some of these problems scientifically? We look into the generalization properties. So if the robot, for example, learned how to fold a shirt, can the same type of representation be also used for unfolding or potentially ironing and so on? We would also like to have representations that are embodiment independent. So it doesn't really matter whether we have robots with two arms that have 6 degrees of freedom each or 7 degrees of freedom each. We would like to understand whether then the representation can be transferred between these various types of embodiments. From the multisensory perspective, of course, we also think that this is very relevant because I think that for context-rich tasks, integrating visual and then forced or tactile feedback comes very natural to us. But proprioception itself, potentially sound, have also a very important role in this, because they can also give us more information about, for example, type of material or success of the task and so on as it's being performed. There are many things we could discuss about continuous, active, incremental, self-supervised learning, and there are portions of these in everything that I have shown. What I still think it's interesting and very open is how do we do this continuous, active, incremental with multisensory data. And the reason for this is that most of the objects robots will need to interact with well, they have properties that are based on their rigid, soft, or deformable nature. And I don't think that only using visual feedback is enough if we really want to actively interact with the objects and change their states. And that also brings us to physical parameters beyond shape. Now, in order to be able to do that, we deploy analytic and data-driven approaches with various types of use of kernels, priors, regularizers, latent space representation, and we use quite a bit of sim-to-real transfer in order to understand what can be learned in simulation and how can we devise algorithms that then bring the model learned in simulated world and adapt it to a real life setup. Now, from the representation learning perspective, it would also, and from the first point on the previous slide, it has to do with generalizable representations. We like to look into how these representations also scale over various types of tasks. So what is common, for example, for representing or the control algorithms used in cutting a squash, doing formation control, understanding how to devise planning algorithms for dragging a human from the water, or doing dexterous interaction and performing tasks such as grasping or caging, and using representation that then allows us to somehow transfer the same model of control over various types of tasks. And here we have used in particular lots of, well, the representations that we use stem from the topological approaches, thinking about how various types of chain interact and how we can achieve safe formation control or safe interaction, caging, by using the same type of representation. This has also resulted in a recent work. This is from this year in Europe, where we also felt that lots of the work that still needs to be done in order to do this transfer of representations of various types of tasks, generating data sets that are relevant for addressing these types of questions. So what we looked into is how we can build environments from rather basic simulations that give us the ability to study how to solve dynamic tasks with so-called topologically non-trivial deformable objects. And I'm going to give you an example of what that might be. So this is soon to be released at GitHub. So we wanted to do something that is scalable and open source, easy to use, based on OpenAI Gym interface, and also very easy to customize so that one can tune material properties such as friction, elasticity, bending. We wanted to simplify the grasping and control so that we define some anchoring points. So we assume that the grasping of these items is then solved. And we also provided a support for loading custom type of meshes, whether the objects are deformable or rigid or combination of these to make an easy use of the system. So what might be the tasks? We looked into various types of difficulty. It might be putting a tube scarf over the mannequin's head, which we consider as an easy task from the representation point of view. Putting a mask over the ears, medium, or putting a backpack with long handles around the mannequin's arms, which requires a pretty rather difficult I would say, motion planning strategy in order to achieve it. And I think that we ended up here because I was really amazed, when you look into somebody buttoning their shirt and just trying to understand how we do that based on tactile feedback and, of course, lots of experience without looking. So, we use one hand to identify where the hole is. We use another hand to locate the button. And then this fantastic interaction between the hole and the button and the fingers, of course, happens. So we would like to understand, okay, what, if anything, is common regarding that representation and executing such a task with various types of embodiments, human hands, but also how would we, of course, do this with robots? What would be the underlying need for dexterity? How many degrees of freedom the task itself has, and so on. So this type of a simulated environment allows us to study various aspects of the complexity and think of what might be then the underlying representation that allows to do effective control. Thinking a little bit about buttoning and how would we also extract this information from humans, if this would be something that we wanted to do, also brought us to the problem of understanding of how to estimate pose and shape of handheld objects from RGB images. So we want to understand how what the hand is doing when interacting with the object, but also relevant for the task that the human is executing. So where are the fingers? We are just to bring the bottle from A to B. So if you move it from a table to a cupboard, for example, or whether you need to apply a grasp that allows you to actually pour the wine to a glass. So these are kind of tasks that may require various types of stability conditions to be fulfilled. Humans don't necessarily think about that, but we know that dependent on how much wine there is in a bottle, the center of the mass of that object changes, and dependent on the center of the mass, also the grasp needs to be applied along the bottle so that the stability conditions are satisfied. And these are the things we would like to understand, how to predict then the 3D hand and object poses directly from RGB images, how we can leverage hand pose estimation in order to understand the pose of the object, and then use the hand to facilitate, again, the object pose estimation, so both at the same time. This resulted in a system that could then allow us to look into real world data sets, interaction again between one or two hands, and various types of tools and objects. So we looked into how the robot or how the human holds a knife when interacting with various types of objects. So thinking now about how to cut the squash or an apple, or whether you peel it, where the thumb is, where the index finger is, and so on. And then use some of these strategies to generate what we call task-oriented grasping in robots. And the problem of actually transferring that knowledge is not so very easy, because robots will not have all the degrees of freedom in their hands as robots have. So the transfer needs to be also done in a manner that satisfies, again, the stability conditions that need to then, again, be used for generating relevant types of grasps in robots. Now, I wanted to say also a couple of things why still and how understanding human motion can help us to also build control algorithms for the robot or for robots in a better way. So when we look into humans and work a lot with tracking human body in various interactions, there are many questions that one would like to answer. where am I? What can I do? How can I move my arms? Anticipating human motion, and then of course also planning. Where should I move my hand? How long should I keep it there, and so on. So there are a couple of interesting questions that relate mostly to human robot interactions. And then classically, we think about how the community also talks about these problems. It's everything from motion generation, motion prediction, motion planning that is very common in the robotics community, to more action and category level action, representation and categorization, as it has been studied in the computer vision community. So the work that we have done or started to do some years back was very much about the prediction, trying to understand, given a couple of frames of the latest human motion, what will the human do next, and how can we learn or generate various types of deep neural networks to predict future motion given past observations. So we looked very much into the representation that might be relevant, thinking about various types of temporal encoders to do that, and that has focused on various types of human body. And this was very important because we wanted to understand how this relates to various types of tasks that humans are performing and that can potentially be relevant also for the interaction with the robot. And then assess various types of temporal models that could then be compared to some form of a ground truth and give us an indication to what extent the model is able to reconstruct upper body or lower body motion, and to what extent the model can encode high dimensionality in gross versus fine motion of the humans. So now this is like 4 years old work. We looked into just maybe 600-700 milliseconds prediction, compared many types of models, trying to understand, as I said, this gross versus fine motion, to what extent boxing is different from walking, and so on, just to try to understand whether a certain model encodes the upper body versus the lower body motion in a better way, and so on. And then we continue to work with this, trying to do longer term predictions, and so on. And there are many things that we addressed, really trying to understand how the aspect of using real data, data that does not provide maybe the full body motion, the distribution over several possible outcomes or several possible motions can be encoded also in how do we put in uncertainty, and so on. So assess various types of conditional variational autoencoders, which is just one example where we looked into what that prediction might be. So the trajectories, the yellow trajectories, are this 1.6 seconds kind of like predictions of what most likely next position of the hand will be. And this is very important again for even industrial setting where we have a robot working very closely to human, that in terms of safety and so on, that the robot should at all times be able to predict what the human is going to do next in order to be able to generate slower motion or well, not to hurt the human, and so on. Let me just skip over this one and go a little bit into then the physical aspect also. I promised to say a little bit about encoding the high dimensional tasks, and tell you a little bit about how to design various types of action policies on robots that are supposed to collaborate with humans, and while keeping also this physical contact with the human, that is an additional challenge, I would say. Just very shortly, the task that we studied initially, how to collaboratively position the ball, minimizing the interaction force. And then about the assumptions, we don't have the assumption of a dynamic model, that all the partners will contribute or collaborate equally, and that we try to do this adaptation from very few examples. So this is just how it looks. To start with generating the training data, both the robot and the human are performing some set of random actions. And the idea here is to bring the ball either to the middle or to one of the ends of this balancing setup. And here then, this is how then after just a couple of tries, then from any starting position of the ball, this coordination between the human and the robot is so successful, so that we can find a way of how to then bring the ball collaboratively to the appropriate position. That motivated the work into looking more into deep predictive policy training and also using reinforcement learning, where we in particular wanted to do this in higher dimension. This is why we started to look into throwing, grasping, and so on, and how we can, to what extent we can push the use of reinforcement learning techniques to learn complex behaviors with qualitative terminal rewards, where after each trial, we would just say to the robot, yes, this was a good example, or no, that was a bad example. And also already back then, we looked into how to model then the whole, or build the whole learning framework that is based both on simulated and synthetic data. So this is, again, just one example here. This is the video that I already showed you. So I wanted to go through is the way of how do we build then a system that is based on a cascaded set of encoder, decoder networks in order to be able to do this just from a couple of trials, I think, not using more than an hour of training or something like that. And the motivation here is that in most cases where the robot will need to learn tasks from scratch, we will not be able to, for very dynamic tasks, let robots to just test this very freely, especially when, as I said, interacting with the environment, because the robot can break and so on. So the system is based on visual feedback. So we have input RGB images. We have some form of state representation that is then used to model what we call an action manifold that allows the robot to then generate a behavior that is a set of then joint motions temporally in order to generate a swinging motion. So to give you a little bit of an idea how it works, so the input observation image, rather small, 200 by 200 pixels, and then the motor trajectory would be then controlling 7 degrees of freedom along maybe like 20 time steps. But you can understand the size of the space. So if you would need to populate that space in between and learn the mapping between this space and that space, it's very high dimensional. It would require very many examples. So what we said was that, well, but the robot, independent of what kind of swing it generates, it will usually go through very similar a set of or combinations of joint angles. So there needs to be some lower dimensional representation of that. And then, of course, we can also encode the position of a target in a lower dimensional space. So that was the idea. How do we then learn encoding of the lower dimensional representations, but then train the relationship between the perception and the action in this lower dimensional encoded space. So that was one of the approaches we had. So first we start with the perception model training. We have an input image that uses an encoder decoder structure. So this is the output image, you see it here. So the idea is then to just keep the encoder part that is then, that has learned this lower dimensional representation. And then, so we throw away the decoder part, and then we do something very similar for the behavior super layer, but the vice versa. So what we say here is that in particular, we keep the decoder part. And then the action trajectories, they can also be generated in simulation. And they basically come from a blind controller that doesn't have a target, just to basically learn the combination of relevant joint angles. It might be for grasping, it might be for pushing, it might be for drawing, and so on. So then that behavior super layer will be basically a trained decoder, and we can see it as an auxiliary model to train it, where the policy is not kind of like included. And then again, here we then see that the basic idea of how much smaller than the mapping space would be between the perception and the action part. Sorry, I thought that I muted all my videos. So then the policy learning, or the policy super layer, map states to points in the action space. It's trained with policy search, reinforcement learning, and then we really don't have the temporal complexity, because we actually do the mapping to full trajectories. There are only few parameters that need to be learned, and that can be done with qualitative rewards, which are based here. And then let me mute both of these. So we demonstrated this on a couple of tasks. One of them was, as I already said, throwing. The other one was grasping, so that the robot would learn from about 250 trials, just using two or 3 hours of training. And then the work that followed basically addressed many of ideas that we did in this initial work, just to show how would we now generalize and have the representation for various types of tasks that can generalize then over a set of tasks that have similar properties. So let me then, in the interest of time, go a little bit back into what I have already said, and just try to summarize my talk, give you also a possibility to ask questions. So I still think that robotics and working with real physical systems both motivates lots of research from the perspective of generalization. So try to look into contact-rich tasks that we humans do on daily basis, and with the development of right set of benchmarks, either in simulation or into the real, or in the real kind of on real physical systems, motivate and demonstrate how task relevance and generalization are both important, but what kinds of methods we could employ in order to show that a certain model is valid over a set of different tasks, what can be transferred, and how we can also efficiently represent complexity of the tasks so that the generalization is possible. One of the big challenges in robotics has been that transfer also is valid over different types of embodiments. Now, I don't think that we should be addressing impossible tasks of expecting that the robot with 2 fingers will be with the exact same motion, be able to do what a robot with a 4-fingered hand can do. No, I think that the strategies of using the dual arm setup in combination with rather simple hands will do things differently than a robot with do all our setup in rather extensive hands, but I think that there is still something in the representation that can be maybe shared or showed how we can incrementally extend the representation and adapt it to a more complex embodiment. And the reason, maybe not the reason, but the motivation is like if we think about ourselves, what happens when we, for example, injure one of the hands or one of the fingers or one of the arms, we are still able to execute things and tasks in our kind of like daily life, maybe not as efficiently, but there is something, we at least share the goal. We need a little bit more time maybe to execute them and so on. But there is still something that is common, independent of whether we do things with a hand that is fully healthy or maybe with a hand that has injured 2 fingers or something like that. We humans also do all this by using multisensory data. I think that visual feedback is very important, but using haptics, using sound, using smell, and so on is definitely something we need to also think of how to encode and represent in all the models. That will then give us a better way of also addressing problems related to continuous, active, incremental, self-supervised learning and so on. I would also like to see more work that addresses the problem of interaction with rigid, soft, and deformable objects, because I think we have spent quite some time addressing physical interaction with rigid objects, but doing deformables is something completely different. So we need more work on that. And also in relation to that, how to address the problem of modeling physical parameters beyond shape. And as I said, I don't think that any of the communities, if I think about computer vision, control, signal processing, machine learning, robotics, AI will do it on their own. I think that we just need to learn how to use models and ideas in between communities in order to be able to solve some of these problems efficiently. That's all from me. I think I will stop sharing my slides now, and if there are any questions, I would be happy to address them.